Let's begin now by looking at the concept of damping and resonance. Okay, so because we have already looked at the fundamentals of waves, okay, so it's important for us to look at what happens to a wave if it is allowed to, if it is allowed to oscillate, okay, for a very long time. Okay, and in this world, okay, there is no such thing as a wave that goes on forever and ever and ever lah. Okay, after a while, when you start oscillating something, if you don't push it, it will, after a while, it will come to stop. Okay, just like if you have a baby and then you put the baby in the rocking spring, right? Okay, if you don't keep pushing the spring, okay, after a while, it's going to stop. Okay, what is happening is, the amplitude will decrease. Okay, you're going to find that the amplitude is going to decrease. Okay, means let's say if it is swinging like this, like this, like this, then after a while, you find that the amplitude decreases. So again, if you if you like, what is amplitude, sir? Okay, then go back to the first subtopic lah. We've covered this in the fundamentals. So words like wavelength, amplitude, period, frequency, wave speed, all this, okay, should be familiar to you by now. Okay, at least you have an idea of what I'm talking about lah. So you find now that if, let's say, the mother stops pushing the baby's the spring, okay, the amplitude is going to decrease and it's going to stop at last. So the question that we need to ask is, what is it that makes the cradle stop oscillating after his mother stops swinging? What causes the cradle to stop swinging? And that's what we call damping. Okay, damping dalam bahasa Melayu is called pelembapan lah. Okay, pelembapan. Okay, as in, damp. Okay, so let's talk about damping for an oscillating and vibrating system and resonance. Okay, take a look at this video.
Have you been on a swing in the playground? What can you say about the amplitude of the swing? What can you do to maintain or increase the amplitude?
Okay, so the question is, what can you say about the amplitude of the swing? And what can you do to maintain or to increase the amplitude? What would you do? Can anybody give me a suggestion? If you want to maintain the amplitude, if you want the boy to keep on swinging at the same amplitude, what should you do? Anybody?
Keep applying energy.
Okay, you keep applying not energy but a force lah. Okay, you keep applying a force. You keep pushing it. Okay, so that so that it doesn't stop. Because if you don't push it, of course, this boy, there is a way for you to push yourself without somebody pushing you lah. But okay, if you don't apply a force, if you don't apply a force, okay, then after a while, the boy is going to stop swinging. The amplitude is going to decrease. Okay, let's take a look at another video. Okay, so you find that when this is swinging, okay, and we look at it, go up and then go down and then go up and then go down. Then after a while, we find that the amplitude is decreasing. Look at the amplitudes. Okay, it is decreasing. So what can you say about the amplitude? The amplitude, at first, it oscillates with maximum amplitude. And then after that, the amplitude decreases with time. Okay, the height of the wave, okay, decreases with time. So again, we use the words amplitude over here. Okay, so what causes the pendulum to stop? Okay, anybody want to suggest? What do you think? I know it's called damping, but what if I don't tell you the word damping, right? What do you think causes this pendulum to stop swinging?
The energy dissipate already.
Why the energy dissipate? Why did the energy dissipate? Energy dissipate
because energy don't have
because of air resistance.
Oh, okay. So Ethan has been replaced by Rahman. Okay. I like the fact that Ethan says energy dissipate. I think that's a very important thing. Okay, but one thing that we've learned in Form 3 is that energy, actually energy doesn't disappear. You cannot create energy and you cannot make energy disappear. It just transforms from one bentuk to another bentuk to another bentuk lah. Okay, so when you say energy dissipates, it has to dissipate because of something. It is doing something, or it is being transferred to something. And I think Rahman has the good idea over there. Okay, it is because of the air resistance. All around this pendulum, okay, there is air all around. And and the air is actually stopping the pendulum from oscillating as much as it can. Okay, and so we call this air friction. I'm not really sure what Chloe was trying to say. Were you going to say something, Chloe? Was it Chloe saying something? I heard a girl's voice.
Yes, it was me.
Oh, what were you saying?
No force, lol.
Okay, there's no force. Yeah, actually it's true. There's no force because all the energy, okay, as Ethan said, okay, has been transferred over to the air molecules so that the pendulum can try to continually move. But in doing so, when the energy is being transferred or dissipated into the air, okay, it loses energy. Okay, and it loses energy, therefore the amplitude of the pendulum is decreasing. So why does it lose energy? The short answer is it's air friction. Okay, I like the fact that they use energy dissipation. Good. All right. So, oh dear. Okay, so the same thing we see over here. Okay, so when the pendulum oscillates, okay, it has energy. Okay, and so the energy is used to overcome air friction, which is, what I think Ethan was trying to get at. And so as time passes, more energy is being used to overcome air friction. So the pendulum is going to lose its energy. Okay, and this causes the energy of the pendulum to decrease, to dissipate. Okay, and therefore the amplitude becomes smaller. If you remember in the question that we saw on Monday, I said that when we talk about the energy of a wave, we look at the amplitude. Okay, the bigger the amplitude, the higher the energy of the wave. Okay, and so what this is called, okay, is called damping. Okay, the loss of energy due to air friction. Okay, the loss of energy, the reducing amplitude because of the air friction, okay, is what we call damping. Okay, so damping in the damping effect in the vibrating system can be seen in this particular experiment over here. If you have a plasticine on a saw blade, okay, and then you oscillate it okay, back and forth, you're going to find that the amplitude of the vibration is going to decrease. Okay, and so we find that there's a relationship between the amplitude of the vibration with time. So the amplitude decreases when time increases. The bigger the time, okay, the smaller the amplitude. Okay, and just to remind you that the period, okay, the time for one oscillation is from Z to X and then back to Z again. Okay, that is one oscillation, satu ayunan penuh. Must go back to the original starting position. Okay, and so what is a possible reason for the answer in 3? Ethan has the right answer just now. The energy has decreased. Okay, so what happens to the energy possessed by the plasticine and the blade? The energy is lost, okay, due to heat. Energy is lost to heat due to friction. Okay, one thing that you will hear me continually say in your entire physics career, okay, I mean, if I'm teaching you next year, one thing that you will continually hear me say is that friction causes heat. Okay, and because friction causes heat, energy is lost due to that friction. Okay, anything that bergeser always causes heat. When two people misunderstand each other, they are obviously going to get into a fight. Wow, friction causes heat is true. When two people are at odds with one another, okay, they are going to bergeser with one another and they are going to get into a very heated debate. Okay, that's why when people argue, dia punya keadaan menjadi panas. Nobody, when you argue, dia punya keadaan menjadi sejuk. Kan? Have you ever heard anybody that is annoyed and say, ish, bikin sejuk? Mana ada kan? You always say, ish, bikin panas. And you always hear people say, ish, bikin panas. You don't say, ish, bikin sejuk. It would be so weird if people say, ish, bikin sejuk. Okay, because friction causes heat. Okay, and when friction causes heat, energy is lost because the heat The energy that you have is transferred into heat to overcome that friction. Okay, wow, this is like so many life applications lah. So what happens to the oscillation on the blade after a long time? The blade will stop vibrating. After a long time, okay, it's going to lose all its energy and then finally it's going to stop vibrating. Okay, again, we call this process the process of damping. So the technical definition is this: damping is the decrease of the amplitude of an oscillating system when its energy is drained out as heat due to friction. Okay, I want you to add the words there. I want you to add the words due to friction over there if it is not inside your module. Hold on. Oh, okay, yeah. So what is the meaning of damping? It's there. Okay, the decrease of an amplitude of an oscillating system when its energy is drained out as heat due to friction. Okay, so I don't know why all the animations are coming at the wrong time. So what type of energy is produced due to damping is heat. Okay, and how do you overcome the damping effect? I think somebody mentioned just now, how do you keep the boy from stopping? Is you keep applying a force. We don't apply energy, we apply a force. Okay, when we apply a force, we give it energy lah, but we apply a force. Okay, kita tolak dia. So anything that has to do with push and pull is a force. Okay, so we apply a force so that it can continue oscillating. But if it is damping, this is how the graph will look like. Okay, take note that when damping happens, okay, the graph is going to decrease in amplitude. Jangan juga kamu all the way the same, then suddenly habis. cannot. Okay, the amplitude must be nicely decreasing lah. Okay, all the way. All right, so please take note of how to draw the graph. All right, next. Again, the same thing. There are two types of damping, okay, which is external damping. Okay, so the external damping is oscillating system loses energy to overcome friction or air resistance. Okay, so the types of damping refers to how the oscillating system, okay, loses its energy. Okay, how or why does the oscillating system lose its energy? There are two factors. Number one is an external reason. Okay, and the external reason is the air resistance that we saw just now. But besides that, there is also an internal problem. Okay, there's an internal factor involved. So the oscillating system loses its energy because of the stretching and the compression of the vibrating particles in the system. Okay, think of the spring just now. You know the spring that had the baby just now? Oh no. Okay, fine. Baby is in here. Oh my goodness, what a horrible position, but okay, fine. So when the spring is going down and up, down and up, down and up, right? Okay, think of the molecules in the spring. Okay, the molecules in the spring will be sekejap, they will be very close together, and then sekejap, they will be very far apart. So they will go back and forth between this. Nearer compression. Okay, so this is compression, ini. And then stretching is this one. Okay, compress, stretch, compress, stretch, compress, stretch. Okay, imagine if I ask all of you, all 23 of you, okay, I ask all of you to stand in the field and stand in a straight line, and then I ask you to hold hands. And then after that, okay, somebody on each side start to compress you, start to run in and out, in and out, in and out. Okay, all of you in the center will be like, oh, this is so tiring, you have to keep doing this and this and this. Okay, to compensate for what is happening at the side over here. And that makes you lose energy because you have to constantly compress and stretch, compress and stretch, compress and stretch. Okay, and that makes it lose energy. And we call this internal damping. So at the beginning stage, when I was talking about this, I said that, you said that one of the reasons why damping occurs is because of air friction. Okay, and that one we call external damping. But now we want to level up our knowledge. we want to say that it's not just air friction, it's not just outside factors, it's an internal problem as well. Okay, internal problem is the molecules in the system, okay, have to constantly move and stretch and compress, stretch and compress. So because of that, okay, it's going to lose energy. Okay, and that one we call internal damping. So external is because of air friction, internal is because of the losing of the energy of the molecules, okay, due to stretching and compression. Oh dear. Sorry. So damping is the reduction of amplitude. Same thing now, okay, in an oscillation due to the loss of energy. During damping, the oscillating frequency remains constant while the oscillating amplitude decreases. Okay, this is what I want to mention now. Look at the frequency. The frequency is the same, okay, because the wavelength, technically, okay, the wavelength is the same distance. Kan? So highlight this in your notes. The frequency remains constant, but the amplitude decreases. A lot of people think that when amplitude decrease, the frequency also decrease, which is not true. We said this in Monday's class. Remember the speed formula, V equals to F lambda? Okay. Frequency and wavelength affect one another. Amplitude doesn't. Okay, the amplitude is just the amount of energy inside a wave. But the wave speed is affected by two factors, which is frequency and wavelength. So you need to make sure that you know this. Okay, the frequency remains constant. Okay, let's take a look at exercise 1. So this is the example just now of the baby, rocking back and forth. So mother puts a baby to sleep in a sarong cradle. Okay, and sorry, why Raman? So I don't know how many of you have this experience. Okay, but if you have ever slept on a hammock, you know what's a hammock? Yang there's a word in English. No, there's a better word in English for the hammock. Like you have a pole over here, and then you have a pole over here, and then you have this bed over here, that you tie a string. Then this one sometimes it's made of cloth, and sometimes it's made of fishing net. Some kind of net lah. Then you sleep on this. It's very relaxing, I know. Have you ever slept on this before? I don't know.
Yes.
Yeah, it's very nice and very relaxing. Yeah, feels like you're flying. You're right. Okay, but it's very shock lah. Okay, so I can imagine why the baby is sleeping so soundly, because I also would lah. But of course, it is more shock if somebody is pushing you lah, right? If you're just standing down, then you keep pushing yourself back and forth. It's pretty annoying lah. When somebody is pushing you and somebody is rocking you to sleep, okay, sure you'll fall asleep. So what happens to the sarong cradle when the mother stops moving the cradle up and down? Okay, obviously damping is going to happen lah. Amplitude of oscillation of the cradle decreases. This is very technical. Okay, amplitude of the oscillation of the cradle decreases and it will finally stop. So we need to suggest a reason for the movement of the sarong cradle discussed in A. And the reason is because it is damping. Okay, damping causes the reduction of the amplitude of oscillation. Okay, so question C, what must you do if you want to help the mother to maintain the movement of the cradle? Okay, or if you want to help your mother, okay, maintain the movement of the cradle, you give an external force. Okay, you can't really do much about the internal. Okay, you can't go into the molecules and then put a loudspeaker or hailer, "Hoi, molecules, do your job." You can't do that. What you can do is you can give them a little bit of a push, okay, so that they get this energy. Like motivation lah. Okay, you give the molecules a little bit of motivation, give them an external force, okay, so that they can continue oscillating. So when we explain our answer, this will be this lah. External force to the cradle gives extra energy to the oscillating cradle, okay, to compensate for the energy dissipated, okay, or the energy lost because of the frictional force. Okay, that's what the external force does. Okay, for us, when we think about this, it's like we do this every day. We don't think about the technical aspects of this lah. We just think that, oh, okay, mau berhenti sudah, okay, kita tolak lagi. Okay, we just keep pushing it so that it will continue to rock. Okay, we don't think about it like Why? Why do we have to push it? What is the scientific explanation behind this? And this is why this is why we learn physics. Okay, to give an explanation to the things that you do without even thinking. Okay, you just know, oh, we need to push it so that it can continue moving. We need to be able to explain why. And the why is this lah. The external force gives the cradle extra energy. Okay, so that the energy that is lost, okay, they can replace the energy that is lost. Okay, so that's the explanation for this. All right, now let's talk about this one. So the effect of damping can be overcome by applying a periodic external force on the oscillating system. Okay, the external force transfers energy to the oscillating system to replace the lost energy. All this we've covered lah. Okay, the periodic external force transfers energy into the oscillating. Blah, blah, blah. Okay, now what we call this, when you have to apply a force, when you have to give it a force, okay, we call this situation a forced oscillation. Okay, so another new word for us to learn. A forced oscillation means it is not oscillating on its own, it is not moving on its own. We have to force it to move. Kita kena paksa dia lah. Okay, so dalam bahasa Melayu, it's called ayunan paksa. Okay, we force it to oscillate by giving it more force. Quite interesting, okay, kita paksa dia ayun. Okay, kita paksa dia ayun dengan memberi daya. Not dengan memberi paksaan, okay? English is dia lebih cantik dalam bahasa Inggeris lah. We force it to oscillate by giving it more force. And the two force words there have a totally different meaning. Kan? We force the oscillation by giving force. Okay? This force and this force, two different meanings. Okay, the first force is paksa. The second force is daya. Okay, so force oscillation happens when you force something to oscillate. Okay, by giving it a force. Okay, so if you take a look at this boy, that is this one, now he's kind of moving without any external force lah. Okay, so we find that an oscillating system that is displaced and then left to oscillate without the action of external forces will oscillate at its natural frequency. Okay, so this is another new word that we need to talk about, natural frequency. When there is no force oscillation, when there is no external force pushing it, and if let's say the oscillating system is oscillating without any damping. Oh, hold on, without any damping. Oh, no, cannot. Sorry. Please scratch that. Okay, natural frequency lah. Okay, an oscillating system that is displaced. Okay, kalau kita tarik dia ke belakang sini kan, lepas tu kita lepaskan. Okay, and then when it is oscillating, it's going to oscillate at its natural frequency. Okay, so this causes resonance to happen. Resonance occurs when a force is applied to an oscillating system at its natural frequency. Different objects have different natural frequencies. Okay, and so resonance is a situation where there is an external force. Okay, there is an external force that is being applied to an oscillating system, and it is forcing the oscillating system to oscillate at its natural frequency. Okay, let me show you an example of what this looks like now. Okay, so this is a situation, we call this Barton's pendulum. Okay, because the guy who discovered this is called Barton now. So there are 1, 2, 3, 4, 5, and there are 5 gold color pendulums. Okay, and there's one silver color one at the side here. Okay, I want you to take a look at what happens. Okay. Sorry.
Right, welcome to Barton's pendulum. On the right, we have a large pendulum, and on the left, 5 different pendula of different length. So, Jacob, would you be so good as to start the large pendulum going? And what I want you to look at is how the amplitude of the various pendula changes, and see if you can identify which one has the largest amplitude. How does that compare to the length of the driver? Let's just take it from here. I think this might be a bit more obvious as to which one has got the biggest amplitude.
Okay, did you see what was happening just now? So this one, okay, the one at the side over here. Okay, so this one over here is what we call the driver pendulum. Okay, and then these are all up, they will definitely feel the effects lah, because they're all connected by a string. Okay, so when this one starts to oscillate, we find that this one is the one that oscillates with the maximum amplitude. Okay, the rest also oscillate a bit, a bit. They also oscillate a bit. Okay, but only one is very significantly oscillating at the maximum amplitude. Okay, and so the explanation behind this okay, let's take a look at the activity to explain this. Okay, sorry, the answers have come up before the questions again. Okay, so which two pendulum are the same length? Okay, it will be D and C. Okay, notice that they are the same length. Okay, now because they have the same length, they will have the same natural frequency. Okay, because they're the same length. Okay, C and D. So when C is pushed, okay, what happens to all the other pendulums? The other pendulums will start to oscillate because the energy is being transferred into the rope. Okay, this one, when we oscillate, so the energy is all transferred, transfer. Okay, transferred to the rope. But only one pendulum will oscillate with a very big amplitude. And we find that it is the same pendulum that has the same length, juga dikenali sebagai the same natural frequency as the one that you push. Okay, the driver pendulum. Okay, so why does this happen? Okay, let's take a look at this. So which two pendulums will continue to oscillate even when other pendulums have stopped? After a while, B, E, and A are going to stop. Okay, and so what happens is pendulum C and D have the same natural frequency. So pendulum C causes pendulum D to oscillate at its natural frequency, and we call this a forced oscillation. Okay, forced oscillation by pendulum C causes pendulum D to oscillate at its natural frequency. And so pendulum D receives a bigger amount of energy and oscillates with the maximum amplitude. Okay, so a forced oscillation at a natural frequency, at the same natural frequency, is what we call resonance. Okay, is what we call resonance. In today's very annoying Gen Z and millennial speak, okay, it is the stand lah. Okay, like wow, I stand. Okay, or I think you guys call this what, the plus one. If somebody says something that you totally agree with, okay, or you totally can stand with that person, or you can totally identify with that person, okay. For example, if let's say somebody in this class says, "Oh, Sir Marcus gives so much homework," and then everybody plus one, or stand. Okay, what you're doing is you are resonating with one another. Okay, I understand how you feel. I know exactly how you feel. Okay, I stand with you. Okay, plus one. Okay, and that's the idea behind the word resonating. Okay, only the people that are in the same situation will resonate. Okay, and the technical term for this is resonance happens, okay, when there is a forced oscillation at the natural frequency. Okay, resonance happens when somebody is saying something, okay, Sir Marcus gives a lot of homework, and then everybody else in the class suddenly starts to type +1 lah, stand lah, okay, dan yang sewaktu dengannya lah, okay, all this annoying Gen Z language, okay, so that's basically it, okay. In the old English, boomers and Gen X people like me, we call this resonate. Okay, last time we don't say, hey bro, I +1 with you, or hey bro, I stand with you. No, last time we say, hey bro, I resonate with what you said. Okay, because we are more sophisticated that way, like that. Okay, so during resonance, during resonance, the system oscillates with a natural frequency, and when the system oscillates with natural frequency, okay, the system will oscillate with maximum amplitude. Two very important things happen when there are things that resonate. Okay, when the system is resonating, the entire system will oscillate with its natural frequency. Natural frequency means no need for external force. Okay, to continue to keep it pushing. Okay, and not only that, when it is oscillating with natural frequency and resonating, it's going to oscillate with the maximum amplitude possible because they have the support. Okay, so if I give you this situation, A, B, C, D, and then this is my driver pendulum. Okay, between A, B, C, and D, which one is going to resonate with X?
C.
Okay, it's going to be C because they have the same natural frequency. Okay, anything with the same natural frequency, okay, is going to resonate. So that's the meaning of resonance. Resonance occurs when a force is applied to an oscillating system at its natural frequency. Okay, so correct, there is no external force in that sense. Like there's no one outside pushing, but there is a force that is being applied at the natural frequency. Okay, that's when resonance occurs. Now we see this in sound. Okay, and let's say you have this sound, you have these two tuning forks. Okay, and you strike a tuning sorry, you strike a tuning fork P, okay, with a hammer. It's gonna have a sound like that lah. Okay, and then you move this tuning fork Q away from tuning fork P without touching the prongs. Okay, let's see what happens. Okay, so what you saw, okay, in the video just now is exactly an example of resonance. Okay, so why does the tuning fork Q, okay, produce a sound when it is not even being touched? They are not even touching one another, and yet, you will find that Q has a sound, unless you add the weight lah. Okay, that one changes things lah. But since P and Q are identical, okay, very important, both tuning forks will have the same frequency, otherwise known as the natural frequency. Okay, and so when we hit the tuning fork P, okay, when we hit the tuning fork P, it's going to force the tuning fork Q to vibrate in resonance because they have the same frequency. So what's going to happen is when you hit this one, like that, the sound waves are going to travel and hit this tuning fork Q. And because the traveling waves have the same frequency, okay, as the natural frequency of Q. Frequency, not amplitude. Okay, the frequency of the sound waves is the same frequency as the natural frequency of the tuning fork Q. So tuning fork Q will start to vibrate. Okay, when there is a wave coming at you with the same natural frequency, you will oscillate together. Okay, so energy is being transferred from tuning fork P to tuning fork Q. And therefore, tuning fork Q will vibrate with maximum amplitude and produces a sound that can be detected. Okay, notice the order of things. Okay, when resonance happens, maximum amplitude vibration happens. Okay, how does resonance happen? When something that is not vibrating is forced to vibrate at its natural frequency. Okay, bila dia kena paksa untuk menghayun okay, pada frekuensi aslinya, at the natural frequency. Okay, then it's going to resonate. How do you force this one to oscillate with or to vibrate with its natural frequency? You provide a sound or you provide a wave that has the same frequency as the natural frequency. That's why in the second one you saw just now, the guy added a weight over here. Okay, he put a weight over here, and when that happens, okay, the natural frequency has changed already. Okay, it has become a different natural frequency because suddenly it became heavier. Okay, different natural frequency. So when different natural frequency, when you hit this, okay, the wave, the sound wave with already its own frequency is going to hit this tuning fork with a different frequency, different than the natural frequency now. Okay, so yes, just like this, it will also vibrate a little bit, but it will definitely vibrate with a different a different frequency altogether. And that's why when you put it together, you saw in the video just now, you get the two sounds like woo, 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 okay, because they're not the same anymore. But when they are both resonating, they will have the same sound. Okay, just like, if you support one another, you will have the same opinion lah. Okay, although everybody else may not agree, but fine, you have the same opinion. Okay, because you resonate with one another. Okay, this reminds me of that. What is that Frozen song? I think Love is an Open Door. The one where it says, I think it's crazy, but we finish each other's sandwiches. Okay, it's like they resonate with one another because they have the same natural frequency. Oh dear, what a horrendous example this is. But yeah, okay, like that. Okay, let's talk about other applications of resonance in our daily lives. Okay, let's take a look at this first.
Dr. Smith has a wine glass that has no decorations and very thin walls. Such a wine glass will give a loud and clear sound when tapped and will create standing waves in the glass. However, creating standing waves in a wine glass is not as easy as it looks. Rubbing a dry finger along the rim of the glass provides too much friction, while rubbing a very wet finger does not have enough friction. Rubbing too fast does not work. Rubbing too slow does not work either. The finger must be rubbed along the rim of the glass with just the right amount of moisture, pressure, and speed in order for the correct amount of energy to be transferred to the glass that perfectly matches the energy of the natural resonant frequency of the glass. Remember, standing waves are actual physical oscillations in the object, so Dr. Smith can only hold the glass at a node. If he holds the glass somewhere else, the standing wave will dissipate its energy into his hand, stopping the generated sound. You can easily change the natural frequency of a wine glass by adding water. The addition of water changes the mass of the glass, and with more water, a lower natural frequency resides in the glass. If you look closely at the edge of the water in a resonating glass, you can see standing waves being created.
Sorry. Okay, sorry, I don't know if you recognize the song that he was playing just now, but it is from Star Wars lah. It is the Imperial March, Darth Vader's Imperial March. But do you notice that in the video just now? Okay, that's an example of resonance lah. Okay, when you push your finger against the glass, okay, you are forcing it to vibrate at its natural frequency. And when you add the water, the natural frequency changes. Okay, the more water you add, you are decreasing its natural frequency, and that's why the sound becomes lower. It doesn't become softer, okay, it becomes lower, okay, because the frequency has changed. I said this in Monday's class, high frequency, low frequency, okay, so same volume, but it's just, the tone tells you the frequency. So when there's no water in the glass, we call it the high frequency situation. That's why the sound will be very high lah. Okay, but when you add more and more and more water, you are changing the natural frequency of the system. Okay, and that's why the addition of water will cause the sound to be much lower. If you have wine glasses at home, and this can only work with certain type of glasses lah. Definitely cannot work with paper cup and plastic cup and the mugs, it doesn't work. Okay, it needs to work with only certain glasses, and when I do this, I usually find that wine glasses work the best because of the shape of the wine glass. If you drink, okay, if anybody in your family drinks, so like the whiskey shot glass, all those glasses don't work because of the shape of the glass. So the wine glasses work the best, or a round bowl, a round glass bowl. Okay, that works also very well. So you can try this. Okay, you can try this to see the effect of resonance. Okay, let's look at another video. Okay, same situation, but
Just recording, okay? It's true.
whether this is the end. Oh no, it's not the end. Okay, so if you want to know more, please go and go to the website www.theglassduo.com. They are actually very cool. Okay, do you notice that they had different shaped glasses? Okay, they didn't just change the height of the water, but they also changed the size of the glass in order to create a more complete instrument. Okay, but what they're doing, if you notice when they were playing, the entire time they were dipping their hands in the water just to make sure that they had the same consistency of the liquid on their hands. Okay, pretty cool. Okay, resonance. Okay, this is probably the most famous example, okay, of resonance, which is the opera singer. Okay, but instead of opera singer, we have okay. So we find out that if you have watched a video from YouTube about a breaking glass with a high pitched sound, we find out that actually it is not the volume of the singing that causes the glass to break. It is actually the frequency. Okay, when you find a glass, okay, and you are able to sing at the same frequency as the natural frequency of the glass, your singing is going to cause the glass to vibrate on its own. Okay, and the longer it vibrates, remember, vibration causes compression and stretching, compression and stretching, compression and stretching. So you know the glass is going to break because after a while it cannot tahan already because you keep forcing it to oscillate. Okay, and it's possible to happen, but the problem is finding the natural frequency of the wine glass. Different glasses, different ketebalan glass have different have different natural frequencies. Okay, so yes, it is possible for somebody to sing and make the wine glass pecah, but it's very difficult because you need to sing at a very high frequency. If you saw the video at the first video, the one where they showed the frequency analyzer, that particular wine glass has 1K, no, 1000 hertz. That is a very high frequency. Okay, not many opera singers can even reach that frequency. Okay, let alone maintain it in order to break the glass. It is possible, but it is a bit difficult. So the high pitched sound causes the glass to start vibrating with the same natural frequency. Okay, the glass vibrates at its maximum amplitude because remember, when resonance happens, okay, the thing that's gonna force to vibrate has to vibrate with a maximum amplitude, and that causes the glass to break. Another very common example that we see is the Tacoma Bridge. Okay. Oh, sorry. Okay, and so what is happening here is that the wind, when it is blowing, okay, it happens to have the same frequency as the, sorry, this is not correct. This is the natural frequency, okay, of the bridge. And that's why you see the bridge is oscillating with maximum amplitude, because it happens to be being blown by a wind that has the same natural frequency of the bridge, okay, of the bridge itself. Okay, and that's what caused the bridge to robo lah. And this was way back in 1940 lah. Okay, bridge technology has become significantly different now. Has anybody been to the Sky Bridge at Center Point? Seems to be trending around Facebook now because of the dead end, right? Okay, here's another one. Okay, so the London Millennium Footbridge. It's pretty scary, yeah. That if you were to be walking on a bridge that you think is supposed to be stable, suddenly it starts wobbling and wobbling and wobbling about. It's pretty scary, but it can happen. Okay, if you saw the video just now, there were 2,000 people walking on the bridge at the same time. Okay, and the movement of the 2,000 people can actually cause it to wobble, because the movement will cause the bridge to vibrate at its natural frequency. Okay, I think there was and I'm not sure whether this is a true story, is the group of soldiers that were marching on the bridge. And because, when they march, they have to march together, right? So apparently the marching was the same natural frequency as the natural frequency of the bridge. Okay, and that caused the bridge to vibrate. And then finally the bridge pecah, and then all of the soldiers fell into the water. I don't know whether this is true. Okay, sorry, a few more minutes. Resonance in musical instruments. Okay, this is very normal. Musical instruments produce sound, okay, because of sound waves. And resonance happens when you play an instrument that has the same note. Okay, and this is very clearly shown in a guitar, which I cannot show you now because we are running out of time. But I will show this to you on Friday. Okay, yeah, I know, at 7 o'clock in the morning. I will show this to you on Friday about resonance in a guitar. Okay, when you plug a string that has the same frequency as the string next to it, okay, you're going to see resonance happen. Okay, that's one. So this is one. Well, we're getting a lot of performances today. But... Okay, sorry, I don't know why we're repeating this video lah. Oh no, this video is on loop. Okay, but basically, what is happening here is that when she plays the instrument, it's going to be vibrations. It's going to cause the air and also other parts of the violin to resonate as well. That's why a violin, although it's so small, can produce a very big sound. Okay, last one, radio. Okay, so radios have antennas, okay, that is always, dikelilingi dengan gelombang radio lah. Okay, so every radio station has a different frequency. And so when you adjust the radio, and the radio happens to be vibrating at the same natural frequency as one of the radio waves, that's why you can hear the radio stations playing with you. Radio stations playing on your radio lah. So for example, if the radio station is 89.5 megahertz, okay, your radio waves, okay, that is being received by this antenna, okay, is also 89.5 megahertz. Okay, you're actually forcing this antenna, okay, to vibrate. Okay, so that it can receive the, hold on. Yeah, okay, so resonance happens when the outside frequency is the same as the frequency of the radio. Okay, so the radio itself, okay, has, you know, when that's why when you switch this one or when you press the button now, okay, nowadays you press now. When you press the button, you change the frequency. So when you change the frequency and the frequency happens to be the same as the frequency from the radio wave outside, it's going to come in. Okay, all around us is different radio waves because there's so many different radio stations. Okay, so one radio station, one wave. Another radio station, another wave. Okay, that's why frequencies are very important. Okay, when we're talking about radio waves, the basic application of walkie-talkie. Walkie-talkie also has this same this one. That's why when you turn the channel, this channel, that, right? Actually, what you're doing is every channel has a different frequency. Okay, so if you want, okay, everybody, let's turn to channel 3. So everybody is turning into the same frequency. Okay, so that when you speak, the walkie-talkie that you are listening to will receive the frequency of that particular radio wave. Okay, sorry everyone, I've gone 5 minutes extra. So I will see you all on Friday. The bridge is made from what? The bridge is made from concrete. The Tacoma Bridge, right? The Tacoma Bridge is made from concrete. It's made, no, not concrete. It's made from, you know, tar. Macam jalan raya lah. Definitely not plastic. Okay, that's why the last time this happened was in 1940. After that, now people had to change bridge technology because they had to overcome the natural frequency of the wind. Okay, if you have time lah, okay, I'm so sorry. Please apologize to your next teacher for me. If you have time, okay, please, astaga, sorry. Okay, if you have time, go and research on this bridge. This is an engineering marvel. It is called the Seto Inland Sea Bridge. Okay, I think in Japanese it's called Seto Naikai Hashi. I think so lah. Okay, but this Seto Inland Sea Bridge, okay, is one of Japan's longest bridges that connects between the main island and this small island called Shikoku. Okay, and it is an engineering feat because that particular place, the winds are so strong. Okay, you have to watch this documentary on how they built that bridge and how the Japanese were able to overcome all the odds. Okay, to build a bridge. It is one of the very few, if not the only bridge in the world that has 2 levels. You know, the top level is for cars, and then the bottom level is for train. You know, and they are able to do that now on one of the windiest parts, okay, of the sea, okay, in Japan. You really have to watch that documentary, and then you will know that since 1940, that Tacoma Bridge that fell, right, bridge technology has come such a long way, okay, to overcome resonance and to overcome natural frequency, so that when the winds blow, the bridge doesn't shake, and then finally roboh lah. Okay, we have not had an accident with the bridge. Jangan cakap pasal jambatan Tamparuli lah, okay, itu lain cerita. But we have not had a major accident with the bridge since the Tacoma Bridge. Okay, and that was all the way back in 1940. Okay, bridge technology has really changed since then. Our knowledge about resonance and waves has really helped us. Okay, I'll see you all on Friday. Take care, everyone. Bye.